For Lab 5, I decided to analyze the motion of a gymnast rotating around a bar. The purpose of my experiment was to use Newton's second law and the energy principle to predict the motion and change in energy of the gymnast. I found the predicted and observed positions during one rotation around the bar to match very well. In addition, the graph demonstrating potential and kinetic energy gives a logical picture with change in energy. In general, force is equal to mass times acceleration. Starting with the position data of the gymnast on the bar, we can calculate the velocity at each time step. In this case, we have a non-zero force acting upon the gymnast, so acceleration is non-zero, and therefore velocity and position are changing. Another important principle in this lab is the energy principle. This states that energy cannot be created nor destroyed. Therefore, the change in energy will be zero since the energy only transfers between kinetic and potential energy. Kinetic energy, 1/2 mv squared, occurs when an object has a non-zero velocity. In addition, potential energy of the spring, in this case the gymnast, and gravity affect the system. In my model, I set a few key initial conditions like mass, position, and velocity. I also had to set the spring stiffness to a very large number since a person does not have much spring to them. In this case, 775. On the left side of the screen, you can see the spring representing the gymnast rotates in a large circle demonstrating her rotation around the bar. On the right side is a graph plotting the predicted Y positions of the girl. As you can see, the plots match up really well. The predicted graph curve is a little more perfect since no human error of plotting occurs. Another reason is that not all forces like drag force that exist in real life are taken into account in the model. Overall, the model is a good fit, demonstrating one oscillation period from rest to the end of a full bar rotation. I also plotted the changes in kinetic energy, blue, potential energy of gravity, green, potential energy of spring, red, and the total change in energy of the system, yellow. Quite obviously, there is large variation with the curves. As distance moved increases, so does the potential energy of spring and gravity. However, kinetic energy also increases as velocity increases. Notice the large peak in the middle where the gymnast is nearest to the bottom of the bar and therefore with the largest velocity. Most important, however, is the total change in energy. We expect this to be constant at zero since based on the energy principle, energy cannot be lost, only transferred. In the real world, energy of a system can be lost to the surroundings or universe. The universe cannot lose energy. The reason the system or gymnast in this case loses energy is because in order for her to rotate herself around the bar, she must use some of her own internal energy to succeed. This internal or chemical energy is then transferred to thermal energy and lost to the universe. An important note to point out is that we are comparing the gymnast to a spring. However, it is probably obvious to you that she is definitely not one. When rotating around the bar extended, she does have spring-like characteristics, stretching and compressing as she moves around the bar. To compensate for her being human and not a spring, we set the spring stiffness in the code or model to be very high since she cannot physically stretch or compress much. In conclusion, we find that using Newton's second law and the energy principle helps us predict an object's motion. By comparing the gymnast to a spring with stretches and compressions, we can understand the basic physics of how the spectacle of bars can be achieved.